Determine the efficacy of a metal organic framework for a specific mixture separation application. Transient breakthrough experiments are usually conducted in laboratory units with breakthrough tubes of diameters of approximately 5 millimeters. The length of the packed section may be, say, 100 millimeters. The volumetric flow rate at the inlet to the breakthrough tube is of the order of 2 milliliters per minute, and the superficial gas velocity of the mixture flowing through the tube is approximately of the order of 5 millimeters per second. To compare the separation performance of different MOFs, breakthrough experiments may be conducted to determine the productivities of the recovered purified product. As an example, I show here experimental breakthroughs for 1090 mixtures of propine, component 1, and propene, component 2, at a total pressure of 100 kilopascal and a temperature of 298 Kelvin. These breakthrough experiments are obtained with two different MOFs, CIF6 copper TPA and TIF6 copper TPA, shown by the red circles and blue triangles respectively. These experimental data are from these two publications in Angewandte Chemie and in Chemical Science. I give here the relevant information on the mass of adsorbents packed in the tube. For TIF6 copper TPA, 0.51 grams are packed in the tube, and the inlet flow rate is 4 milliliters per minute. For CIF6 copper TPA, the pack length is 0.05 meters, and the mass of adsorbent is 0.488 grams, with an inlet flow rate of 4 milliliters per minute. What is important is to have a MOF that has the highest productivity of purified propene. And if we demand that the propine content is less than, say, 40 ppm, we can use the experimental breakthroughs to determine the propene productivity, and a simple mass balance will show that the propene productivity is the molar concentration of the gas mixture at the inlet, C sub T, which is the total pressure divided by RT, CT times Q naught, which is the volumetric flow rate of the gas mixture at the inlet, divided by the mass of the adsorbent, and the integral from T2 to T1, where T1 is the breakthrough time for the, propine, and T2 is the breakthrough time for propene. So we integrate between T2 to T1, and this is the mole fraction of alkene in the gas mixture exiting the tube. And this is the integral with respect to the time. The integration can be carried out simply using, say, a simple Simpson quadrature formula, and the productivities of purified propene can be calculated. For CIF6 copper TPA, the value is 37.8 moles per kilogram. This is reported in the Chemical Science paper. And for TIF6 copper TPA, the productivity of purified propene is 25.5 as reported in the Angewandte Chemie paper from 2022. That's all very well. I asked the question, can we estimate the alkene productivities more simply by using the ideal adsorbed solution theory? IAST calculations of mixture adsorption equilibrium may be combined with a shockwave model for transient breakthroughs in fixed beds to determine the productivities of purified alkenes. As an example, let's return to the separation of 1090 mixtures of propyne and propene using the two MOFs TIF6 copper TPA and CIF6 copper TPA, blue and red. The shockwave model is an idealized case in which the concentration fronts traverse the column in the form of shock waves, and this model is described in two of my papers. The first one, RSC Advances 2017, the other one in ACS Omega in 2020. Readers may consult my papers for the derivation of the shockwave model. The shockwave model is shown here for the experiments with TIF6 copper TPA and for the experiments with CIF6 copper TPA. The salient features of the model are as follows. From the IAST, for calculations for a feed mixture with mole fractions Y10 and Y20 at the inlet. In this case, we have Y10 equals 0.1 and Y20 equals 0.9. We can determine from the IAST the component molar loadings in equilibrium with the partial pressures in the bulk gas mixture entering the adsorber, and the component loadings are respectively Q1 and Q2. Q1 is for propene and Q2 is for, I beg your pardon, Q1 is for propyne, component 1, and Q2 is for propene. The component loading Q1 for propyne is simply equals the mole fraction of propyne at the inlet, Y10, times the molar concentration of the gas mixture at the inlet, Ct, times the volumetric flow rate, Q0, divided by the mass of adsorbent, times the breakthrough time, T1. So from the shockwave model, we can use the IAST calculation of Q1 to determine the breakthrough time T1. During the time interval delta T, purified propene can be recovered, and the productivity of purified propene is given by this expression, delta Q equals Ct, total molar concentration of the gas mixture, times Q0 divided by mass of adsorbent times delta T. And this delta Q can be determined from the IAST calculations of Q1 and Q2, and this is the formula. So the productivities of purified propene can be determined from IAST calculations, provided we resort to the simplified shockwave model. The calculations of delta Q values for the productivities are respectively for CIF6 copper TPA is 36.2. This is shown here. I beg your pardon. And for TIF6 copper TPA, the productivity value is 31. For TIF6 copper TPA, the productivity determined from IAST is higher than the value determined from experiments. On the other hand, for CIF6 copper TPA, the productivity determined from the IAST is 36.2, whereas the productivity from the breakthrough experiments is determined to be 37.8, slightly higher. The reason for the higher productivities in the experiments is due to synergy between absorption and diffusion. But this is a rather special case. Generally speaking, the IAST calculations of delta Q provide an upper bound to the alkene productivities that are achievable in experimental units.